still thinking about electrical phenomena, and we'll still think a little bit about electric force. Now we reintroduce the other big idea from 2201, energy. And energy, remember, we usually thought of that as a property of a system. So let's imagine a system, a very simple system that consists of just two things. One negatively charged particle and another negatively charged particle, two electrons perhaps. And to keep things even simpler, we'll say that this thing is fixed, glued in place, tied down, not moving. The only part of the system that moves is this one. Okay, now they're both the same type of charge, so they repel each other. So if I want this negatively charged particle to get closer to the other one, I have to give it some kind of a push. And let's say I start pushing at a point in time where the velocity, the initial velocity of this particle is 0, and then I keep on pushing until it gets to this point, so it moves, it feels a displacement like this from the starting point to the finishing point, and then once it gets to the finishing point, I don't move it anymore, I just keep it there, and so the final velocity at the end of this displacement is also 0. Well, my force, my push on this thing did work on this system. And since I'm not part of the system consists of only these two charged particles, my push was an external force. So there's my external push, pushing this way, and it does work on this particle because anytime something feels a force while it's moving, work is done. The particle is moving from here to here, well, it feels my pushing force. And the rule for calculating how much work looks like this. Magnitude of the force is my external push in this case, times magnitude of the displacement. We're really thinking of a simple model here where this particle is just pushed along a straight line from the start to the finish. So in that case, the magnitude of the displacement is just the same as the distance traveled while feeling my pushing force. And then cosine of an angle, and remember, this angle is the angle between the force direction, which goes this way in this case, and the displacement direction. And in this case, displacement points the same way. So in this case, you've got displacement and force in the same direction, so the angle between the force direction and the displacement direction is no angle at all, 0 degrees. So this last factor here is cosine of 0, and trigonometry tells us that the cosine of 0 is 1, positive 1. So the work done is positive. This number is positive 1. This is a magnitude. By definition of magnitude, it must be a positive number. And this also is a magnitude, so just by the definition of magnitude, it must be a positive number. All three factors are positive, so the work done is positive. Remember, positive work means energy is given to the thing that had work done on it. Positive work on this particle means energy is given to this particle. Where did that energy come from? Well, when something gains energy by means of work, that energy always came from the source of the force. So in this case, energy gained by this particle came from me. I'm outside the system. So what really happened here was some energy that was outside the system, my energy, was given now to a piece of the system, this thing here. Some energy flowed into the system when my external force did work on this particle. So, because positive work was done, that moving particle gained some energy, the total energy of that system must have increased. All right, now in this case, any change in the total energy, and there is a change in this case, could come about through some change in kinetic energy and or some change in potential energy, since these two particles are interacting by electric forces. This particular kind of potential energy will be electric potential energy. It'll be related to the fact that these two things have charges. But now think about this, right? Change in anything is just the final value minus the initial value. Kinetic energy is 1/2 mass speed squared. So final kinetic energy is just 1/2 mass final speed squared. Initial kinetic energy is 1/2 mass initial speed squared, but when I started pushing, that particle was at rest, initial velocity of 0, and when I finished pushing, the particle is at rest again. Final velocity and initial velocity both are 0, so that's 0 and that's 0, so the change in kinetic energy is 0. What have we got? Well, the total energy of our two-particle system increased, energy was gained, but none of that energy showed up as an increase in kinetic energy, so there must have been some other type of energy that increased as a result, and that's the electrical potential energy. Now, at this point, let's define a new concept, a new number. I'll redraw this this figure. It's getting a little too full of stuff. So here's that negatively charged particle. It's pretty much staying still, and the only other thing in the system is this, which moves from an initial location here to a final location here, and initially started out with a speed of 0, and at the end ends up with a speed of 0. Now here's where we define a new quantity called potential. It sounds like potential energy, and it's going to be closely related to potential energy, but potential is not potential energy. Potential is not potential energy. Potential is not potential energy. Why am I repeating something that sounds kind of obvious? Because it's another one of those things that is easy to say and understand. It's easy to understand when you say it, but it's hard to remember. It's hard to recognize a situation in which you have to remember that they're two different things. You have to distinguish, be careful to distinguish one from another. Anyway, potential is just some property of a point in space if that point is near a charge. It's kind of like electric field in that respect. Any charged object fills the space around it with electric field, and also any charged object will cause there to be electrical potential at all locations around it. So let's say that where the particle starts out, let's say it starts out very, very far away, far enough away that this particle here that causes there to be electric potential in its neighborhood, this is so far away that it's really almost too far away for this particle to create any electrical potential here. So for all practical purposes, electrical potential at this point, far, far away from here, is, we'll say, is 0. And here's one other tricky thing. We always algebraically represent electrical potential with a V, which of course is what we use for velocity also. I'll try to be careful and always represent potential with a capital V and velocity with lowercase v. So the initial potential, when you're really, really far away from something that could cause potential, is just 0. All right, and then now this particle ends up close to this particle, close enough so that it's at a point that does have potential, because this point actually is in the neighborhood of this point. And here's our basic definition of potential. The potential energy that you get, the electrical potential energy that you get, in this case we got potential energy by doing positive work on this system. The potential energy that you get by, say, putting a charged particle at some particular point where it's near some other particle that is the source of potential. Potential at this point is not going to be 0, because it's close enough to be, this location is close enough to be influenced by this. The electrical potential that you get by putting some charge at some location, we'll call it X. So a charge that we'll call Q, you put it at a location called X. That's just going to be equal to that charge times the electric potential at X, the value of the electric potential at that location. And of course, now here you can see a similarity between electric potential and electric field. Right? Both electric potential and electric field are caused by some charge nearby. The charge nearby fills the space around it with electric field. There's electric field at all points near that charge, which is then the source of all that electric field. And then there's electric potential at all points near that source charge. And then in both cases, the product of some new charge that comes into the picture times that other thing, either field or potential, that product of charge and potential gives us potential energy. And remember, that product of charge and field gave us electric force. So what do we have here? In this case, the change in potential energy is, of course, just final minus initial potential energy. And the final potential energy is just, use this rule, charge times the electric potential at the final location. Minus electric potential energy at the initial location, which is just charge times potential energy, or charge times potential out here, but this this point here was too far away from the source of potential to have any potential. So the initial potential was 0. So all you have on the right-hand side is that, charge times potential at the final location. Or charge times potential at the location called x. So let's write that. The gain in potential energy is just charge times potential at x. But where did this gain in potential energy come from? It came from the work that was done. All of the work the numerical value of work is equal to the numerical value of the energy change. And all of that work went into this. So this number is just equal to the amount of work that was done. And now, with this equation, rewrite it a little bit. Potential at x equals the work done to get this particle from far away to point x divided by the value of the charge. So potential at any point is a certain amount of energy divided by charge, or joules per coulomb. In other words, a number for potential tells you how many joules of work you have to do to move 1 coulomb of charge from far away to that point. Work per, or energy per unit charge, work per unit charge. That's always a good way to think about electric potential. Electric potential at a point is just the work you need to do, the number of joules of work you need to do, the number of joules of energy you need to expend to move 1 coulomb of charge from far away to whatever that point, wherever that point is. Okay. One thing here. I'm saying that the unit label for potential is joules per coulomb. We never actually say joules per coulomb. We never actually say 50 joules per coulomb is the potential. We have another word that we use that is synonymous with joules per coulomb, and that's a word that you all know, whether or not you know what it means. Volts. Our normal unit label for electric potential is volts, where 1 volt is the same as 1 joule per coulomb. And so that's basically why we use capital V for potential. V as in volts. But this rule here, which is just a way of rewriting this rule, is a rule that we'll be coming back to again and again and again and again and again. And the truth of the matter is, and even though there are a lot of equations written on this board, the three equations that actually matter, the ones that you actually need to use, are just these 3. And likewise, when you read through the chapter, you see lots and lots of equations, but the ones that you actually need to use are just very, very, very few in number. So, almost any energy situation that involves electrically charged things, this is important, and this is important. This is just another way of saying this. And then, of course, you have to remember the basic rule for a system's energy change. Work done by the net work done by all the external forces is what changes the system's energy. And then that a change in the system's energy shows up as either a change in kinetic energy and or a change in the electrical potential energy. So this these equations with potential and the fundamental energy change equation really are the only equations that'll matter. Later on, we'll get specific equations for what potential energy looks like in a particular kind of simple situation and what potential looks like in a particular kind of simple situation. But those rules are sort of both closely related to this one.